Hello, everyone. My name is Marco Adolph. I work for TROX, and today we will talk about HVAC systems in the COVID-19 times. And today is the July 15, and this presentation is a build-up from presentations we did the last couple of months, myself and my colleagues. And we are talking about the components of the air conditioning system and how we can use them to reduce the spread of the COVID-19 virus and what we can do in our buildings to keep them safe. This presentation, this video will be divided in three parts, and let's go on. So the idea of this presentation is to have a summarize how contamination control techniques can help in the air conditioning of our buildings, and to understand the basic concept of infected contagious areas in hospitals and what we can do in our general use buildings like commercial and public buildings. We'll see some concepts of contamination control, filtration systems, and all the techniques that are used in the clean rooms. Why we are doing it is because right now we are in the middle of a pandemic and this causing a huge impact all over the world. And it's not the first one and probably will not be the last one. If we look to the history of what happened in the last century, we can see that we had several pandemics and virus attacking the humans, and what is causing that? At the end, to make it spread faster, I think it's because people are more connected, are closer to each other. We're living in crowded cities, and that just makes it easier for a virus or a disease to spread out. And going back to what we have right now, our problem is that the people are infected. The people are in the source of the infection. And this picture came out from a report from Hvac, from the European Air Conditioning Association. And we can see here is our patient or our asymptomatic patient, and he's spreading droplets in the air and also through the fecal matter. And it's quite sure for all international agencies agree already that the transfer from surface to surface and through handshakes, hugs, and really close contact. And there is a big discussion and also a high possibility of the aerosol transmission. And that's in closed environments with several people and lack of ventilation. And can probably get the transmission. That's also the reason so many specialists are asking people to use the masks, everyone to use the masks. So if you have already confirmed the droplets, that means sneezing and coughing against each other. That's the reason we ask everyone to use the to sneeze and cough in the elbow. Also the surfaces, that's the reason we also request people to keep cleaning the hands. Direct contact, handshakes, hugs, kisses, and yeah, that's already found in some areas. The fecal oral transmission, it means the aerosols generated from the bedroom, bringing up all this material. We know that the virus is pretty resistant, so it can live for a long time in surfaces. And yeah, not yet confirmed, but really high likely that it may happen is also an airborne transmission, as the virus can stay in the air for almost 3 hours. Yeah, he loses the capacity to infect with time, but in an closed environment and we keep generating these aerosols, there is a possibility. So talking about the contamination, and now bringing a little bit back to the concept from the engineer and how we will treat it and how we would approach this problem. Contamination is any generic, any substance that falls into our process and our system that's not supposed to be there. It can be caused by external sources, internal sources, and cross-contamination. So pollution, contamination inside of the building, and even the people that are generating all the microorganisms, and from one room to the other. And it can be anything. It can be particle, gases, molecules, ions. And here we have the viable, that's microorganisms, and the virus is classified into that for the contamination control purpose. And yeah, we need to remove this contamination or to control how this contamination moves around the building installation to have a solution or a controlled process. So why it's a contamination an issue? And if we think about an industry, it's because it will damage, reject products, damage our process, reduce our efficiency, reduce our reliability, and it will cause damages, accidents, and illness. And that's the case of the microorganisms in our building. So, and the contamination control at the end, life doesn't have a value, a monetary value. Contamination costs money in the industry, and right now it's costing lives. So we have to deal with that and do something about it. What can be done against contamination? We can control it. To eliminate it fully is really hard, and so we use different techniques to control it and deal with the contamination and minimize it. And when we talk about contamination, we need to be careful, because at the end we need to know what we are dealing with, and we are dealing with really small substance, small objects and things. And just to give you an idea, we will talk a lot about micrometers here. And the 1 millesimal millimeter, so 10 to minus 6 meters. So it's really a small particle. And if you look to a hair, the hair has 50 to 80 millimeters. And any particle that's bigger than 10 micrometers will fall. And from 1 to 10, they will be floating in the air. And if there is no draft or air currents, it will go down. But in our environments, with people walking and people moving around in the air conditioning system, they will stay floating. The particles that are smaller than 1 micrometer, they don't fall at all. And the particles with 0.1 micrometer, that's really small, they have a Brownian movement. That means they don't flow with the currents. They move randomically, and they make really odd and strange movements in the air. For medical interest, we will talk a lot about the particles from 0.2 to 2 micrometers. In clean room testing and evaluation, when we do the commissioning, we use a lot the 0.5 to make the check of the filters and the particle counting. And for the testing of the filters in the US, we use a lot the 0.3, and a lot of the HVAC engineers hear about the filter 99.97% efficiency with the 0.3 particle. Yeah, that's the historically particle used in the US to validate filters. We'll see there are other ones, and there are new trends also in the filter classification. If we look to the particle sizes, the particles that we have, like here's the non-viable, that means the particles that doesn't carry life, that don't generate life, they go to really a wide range of sizes, and we need to treat it, and depending from the size, we will have better methods of treating it. But if you look to the ones that are in the medical range, we have cigarette smoke, we have the atmospheric dust, we have powders from the smoke industry, coal smoke, we have the particles generated by the combustion of the engines. So that's we have a wide spectrum of particles that are in this medical interest range. And why are they so bad? Because they can go into our system, our respiratory system. So they will first cause irritation of our noses, our throat, windpipe, bronchial tubes. And the smaller particles that we will call later on as PM1, the particles that are lower than 1 micrometer, they go into the alveoli, they go into our lungs, and from the lungs, they go in our blood system, and then they can go to our brain, to our organs, and that will generate a lot of diseases. So it can increase the risk of thrombosis, it can generate arteriosclerosis, impairment of birth. So we need to treat the air, and we have been doing it for a long time now. And now we have this new problem. It doesn't change in general how we approach air conditioning, but we have a new threat, and we need to approach it as well. When we go to the to the viable particles, also the microorganisms. See, the range is more or less the same range of sizes that the non-viable particles have. And here we have in the medical part, we have the small particles. We have the penicillin that's not generates the penicillin that we use as a medicament. We have the Escherichia coli, we have the influenza, even smaller is the aftosa virus. And then here we have algae and bacteria and so on. So we need to find a way to filter the bad organisms out of the system of the environment. And yeah, why are these viable particles bad? Because some of them generate sickness, and some of them are airborne. So that means they go in these aerosols and they're floating in the air and they are transmitted by the air. Then there's no need of contact between contaminated person, non-contaminated person. But in the other hand, there is a good thing, because some of these airborne infections, like the common cold, influenza, varicella, they have vaccines and they have treatment. And so that's the reason that we don't hear too much about it. But the one that's still pretty common around the world is tuberculosis. It should be already a solved problem, but it still happens. And that's an airborne disease. So that happens in bad ventilated ambience environments. They are easily spread out. And now we have also the SARS. But not everything that's viable is bad. So we have bacteria that they are good for our body. They are inside of our body. They help our digestion. They have so they are microorganisms that we need to live. And there's a nice study from Professor Noah Fury, and he collected samples of the hands of students, and he found so many different bacteria from different families, and not all of them in every patient. So there's a high variability of microorganisms out there, and some of them are good, some of them are bad. And at the end, what is recommended is, like with all these microorganisms, we should wash our hands with some frequency to avoid like bringing it into our inside of our body and also in open wounds. So we need to wash our hands. And when we go now to the aerosol possibility, and our source is the human, it will happen through sneezes, cough, and our breathing. So when we sneeze and cough, we generate these aerosols. We generate also droplets. The droplets, they are large. They are 0.1 millimeter, so they are not that small, but they go with high speed and to high distances, so to other surfaces, and even people that are like in this distance, and we can hit their faces. And the aerosols, the smaller ones, they tend to be around the source. Some of the bigger ones go down directly. And because of that the distance 1.5 meters, or in US we talk about 6 feet, it came from that, because the small particles stay around here, the bigger one go to the ground. And that's the extreme case, they go far away. And that's also the reason we ask people to sneeze against some surface to keep it around, and to avoid this material to be spread all over the environment. The other thing that's important is that these droplets and aerosols, they are generated, and we get them out, and they have they're in a capsule of humid matter. And if the air is dry, it begins to evaporate the water, and it reduces the size and gets more of this organic matter that's inside of it, and tissue and everything that comes out. And that's what we call nuclei. So the droplets, they can evaporate and transform the nuclei. That's critical also when we are changing beds of a patient room. The droplets evaporated, then we move it around, we put that in the air again. So dry air is bad. So when we look into an enclosed environment, we need to be careful about the humidity of this environment, and we need to control the humidity. And then it comes to the question, how many droplets and nuclei we generate each time? There is no close number yet, but I found a nice blog from Professor Erin Bromwich, a microbiologist, And the estimative is that when we cough, we generate around 3,000 droplets. So every time I cough, I can generate up to 3,000 droplets. When I sneeze, I can generate 30,000 droplets, and small from different sizes. And from just breathing, we generate from 50 to 5,000, but the range is really, really big. When we are breathing, then usually we are not generating a lot of, expelling a lot of the viral matter. We need really to cough and sneeze, and it needs to come from our lungs. Anyway, when we breathe, there are some studies that show that for the influenza, we generate 33 viral particles per minute. But there are experimental studies from observation and so on, but we don't have now, at the moment, data available for the SARS-CoV. So I know there are some guys studying it and trying to find out, but at the moment we don't have this information. So we can assume the worst case scenario that we are generating a lot and we need to deal with a big source of contamination. And from the engineering perspective, how would we deal with the contamination? First of all, try to understand how the contamination can impact. And Herrhauser has he developed a formula. The concept is, okay, to generate an infection, we need to have a doses of a virus or a bacteria. It needs to be in the correct local, or is an open wound or in our respiratory system. How aggressive it can be, how long are we exposed to it, and what is the defense level of our host. So if the host doesn't have a good defense, a lower time, a lower virulence will also cause the disease. So how can we deal with it from the engineering point of view? We can, and what we do usually in the pharmaceutical industry, in the industry that we have to control contamination, we can content, capture, dilute, and control. So that are the four tools that are available for us engineers to deal with the virus. And the first one, if we look to contamination control, is the contention, is creating barriers. And right now for the aerosol possible diseases is the use of masks. And it's already proven, and we have samples of some countries that reinforce the use of the masks from the principal, like the Shanghai, and they have really few cases and few deaths. Taiwan has also did, from the beginning, they started reinforcing the use of masks and some controls, and they were able to do it and keep the business working, and the country more or less normal, except for the reinforced use of masks. And it's important to reinforce it's not just me using the mask to protect myself and expecting that I'm not getting contaminated, but the source of the patient that has COVID need also to be using a mask, because that the mask creates this avoids it to spread around the environment. It stays in the mask. So the use of mask it helps. There are several studies showing it, and it reduces significantly the risk of contamination. And in some environments, and also because we should not put the hands in the eyes and so on, in factories and so on, we are using these face covers, face shields, and we can see that also in the pictures that we see from the hospitals around the world, that the doctors are using the mask and the face shield, and it really avoids and reduces the risk of bringing the hand into the face and touching the eyes and so on. And when we look into a hospital, and when we are talking about the air conditioning, we have to take into account that we can move the air in the direction we want, and that's pretty nice done in isolation rooms. And if it's for an infectious disease, infectious contagious patient, what we do is we supply the air in one point and extract it in other point, and we generate a movement of the air from clean to dirty. And also we supply less air than we are extracting, and then we create a negative pressure in this room and makes the air coming below the door, in the gap of the door, into the room. That avoids that all these droplets and particles that are generated here go to the corridor, and from the corridor to the other rooms. So the guideline that usually we recommend, and that's reinforced here in the US but we recommend all over the world, is, okay, in this case, is the contamination source is our patient. So we need to get the room negative. That means we don't want it going out from this room to the door. We need to protect the medical staff. That means the clean air comes from the medical staff to the patient and then to the extraction. So the extraction will be close to the patient, close to the head of the patient. And the CDC guideline says that we need to have a negative pressure of minus 2.5 Pascal. And for new hospitals and retrofits now, they are requesting that this room has 12 air changes per hour. The supply needs to be done by air filters. Yeah, we need to clean the air that we are injecting into the patient room. And it goes back to the particles that we saw in the beginning of the presentation. The extraction has to be done by a HEPA filter because that's contaminated air. And then we want to keep this virus or bacteria into this filter. The airflow is from in direction of the patient and extract close to the patient. This room has to be sealed, so the windows are not going to be open. And this also, beside the negative pressure that we want here, we will have a difference between supply and extractor of 125 CFM. How we do the control of flows, and we are extracting less than we are injecting, we need to balance that. And we can do it with volume flow control boxes. It can be variable and it can be constant, but if it's constant, it needs to be a damper that's able to deal with variations of the pressure in the ducts. So it needs to be a constant pressure independent valve. The constant valves, they are a simplified solution. They are duct pressure independent, and we need to add a sensor in the room that shows us, because it's a request in CDC, we need to monitor if there is a differential pressure. And we need to have a device that shows that we are keeping the room negative. We can use variable air volume flow boxes, and they will be tracking each other and keeping the control. We have a pressure transducer here, and it shows the valve what it has to do. And we can use the valves that are also applied in laboratories. And then we will have a pressure sensor connected to the valve. We will have, it will be able to react to differential pressure in the ducts. And we can also make it even more complex. We can increase or reduce the airflow changes in this room, because these two valves will be talking to each other, and we will keep the differential flow, and we will be able to keep the pressure. One thing that's important in these projects is that we need to use the same source of reference for all the rooms. Because if we make the reference to the corridor, directly to the corridor and the valves, and someone opens a door here, the pressure in this corridor changes, and all the other valves will begin to float. So it's quite important to have this reference point in a neutral point that's not impacted by environment movement, and it should not be the shaft of the elevator, because every time the elevator moves, this pressure will float in this shaft, and the valves will try to correct something that they don't need to correct, because the room is already working fine. And we validated, we have to validate these rooms. So we do it with pressure transducers in the doors, so when we are doing the commissioning, and also with some smoke devices to see if the smoke goes in the direction that we want the air to go. How can we help with TROX? We have constant volume flow valves of different sizes for different pressures in the room. We have variable air volume flow devices. And we have also the valves that we use for laboratories, clean rooms, and fume hood extraction. And yeah, then we can control and then add control components to it and help out with solutions for it. And we did a small project, a nice project, and not small, so a nice project in this hospital they built in Wuhan in less than 2-3 weeks. We supplied the constant volume flow devices. Were able to control the pressure drop. So here we will finish the first part of this sequence of videos, and we'll come back for the second part.